Now let's continue and solve exam related questions in momentum and impulse. Hopefully through these exercises one is gaining more knowledge, and which is okay. Then let's talk about it, and then so that maybe some of us will gain the valuable knowledge. Now the question that we'll be dealing with now is this question number 5 in this question paper. Relatively very easy question. There's a diagram that is accompanying this. Now they say to the learner, diagram shows two trolleys P and Q held together by means of a compressed spring on a flat frictionless horizontal road track. The masses of P and Q are 400 grams and 600 grams respectively. Remember, in this section of momentum, paper 1, we don't deal with mass in grams. Therefore, immediately you need to convert the 400 grams and 600 grams into kilogram. So you will have the 400 gram, that is M1, which is the same as 0.4 kilogram. Whereas the M2 is 600 grams. Therefore, we are going to use 0.6 kilogram. We divide by 1,000 or multiply by 10 to exponent minus 3. Very important. Now we interpret that one right away. When the trolleys are released, it takes 0.3 seconds for the spring to unwind to its natural length. That is your delta T, which is your contact time, 0.3 seconds. Very important, we'll use it. Now they say to us, the trolley Q then moves to the right at 4 meters per second. Trolley Q, the 600 one. So meaning that now the velocity to initial will be 4 meters per second. So 4 meters per second. Is it the initial? No, it's the final, because initially the velocity was 0. There was no momentum. Fine. No problem. Now they say to us, 5.1, state the principle of conservation of linear momentum in weights. Remember, the principle says now the total sigma Pi equals to sigma Pf. In weights now we'll say the total, because sigma is the total sum. So the total linear momentum in an isolated system. Remember, we said you can start with the isolated system, we can finish with it, or you can put it in the middle. In an isolated system is conserved. Or in an isolated system, the total linear momentum is conserved, or the total linear momentum is conserved in an isolated system. So it depends, as long as the 3 keywords are there. That's the first one, which is your 5.1. 5.1, then let's go to 5.2 and listen to this one. They say to us, calculate 5.2.1. The velocity of P after the trolleys were released. Remember, we know the velocity of Q. Q will head to the right, isn't it? Therefore, no problem. Let's see. We're expecting the velocity of P to be negative because it should head in opposite direction. But let's apply the principle, because there's an explosion here. They were together before, now they are separate after. So this is the first step. Or you can put that one of saying M1 plus M2, yeah, M1 plus M2 multiplied by VI equals to M1 V1F plus M2 V2F. So remember, this is an option, but some way they include both is fine as well. But you can start from here and that go to the substitution as well, no problem. The mark will be given to the principle. The second mark will be for substitution on the left. On the left, they were stationary. There's no need to substitute there. You just put 0. The whole momentum, no movement, no momentum. Now after collision, if this one is Q, then I can know that Q is 0.6 multiplied by 4, and then P is 0.4 multiplied by VF. Then we are calculating VF now using your calculator. You must find that the VF now will be 6 meters per second, negative 6 meters per second. Then we interpret, we know that therefore this will mean that is 6 meters per second to the left, because we take to the right as positive this velocity which is to the right. That's why we take it as positive. If this one is positive, to the left will be negative. So that's the case. Fine, we're done with 5.2.1. Let's go to 5.2.2. Let's see, what does it say? They say to us, calculate the magnitude of the average force exerted by the spring on Q, on trolley Q. Calculate the magnitude of the average force. We know there's only one formula with average force. It says F net delta T equals to delta P. That is the formula. Let's see. There are many ways here, because remember in this case you can find the change in momentum of Q or the change in momentum of P. They will be the same, because according to Newton's third law, it says the force that P exerts on Q will be the same as the force that Q exerts on P. So that's the case. Now let's deal with the first option. Say we are talking about the change in momentum of, in this case, of Q. So it will be F net. The time they said is 0.3. Remember, the spring took that one to react. So the initial momentum, the final momentum, we know it will be 0.6 multiplied by 4, and the initial momentum, it was not moving, therefore F net equals to positive 8 Newton, and that it will be 8 Newton to the right. Fine, you take the right as positive, or you can get the very same to say F net. Now I go for Q delta T equals to delta P. No problem. Now let's go and say F net multiplied by 0.3. Change in momentum, I'm going to use, in this case, 0.4 multiplied by 6, isn't it? That's the final velocity, and then the initial momentum was 0. If I multiply the two, it will give me the same answer, then which will be now 8 Newton, again to the right. I think it's clearer now. So otherwise, others can also use Newton's second law and find acceleration. After acceleration, find the net force. So that one also is allowed if you deal with that. So now let's go to the last question in this case, which is your 5.3. Now 5.3, it say to us, is this an elastic collision? Only answer yes or no. Remember, the golden rule is all real collisions are inelastic. So you should not maybe doubt that one. Therefore, all real collisions are inelastic. Only imaginary collisions, or what we call in the science, we say hypothetical collisions. Therefore, they can be elastic, but all real collisions are inelastic. Therefore, your answer here will be a big no. It's not elastic. But if they were saying prove, then you will find the total kinetic energy before, which will be 0, and the total kinetic energy after, it won't be 0. So that will be the case, because you're going to add the two. Remember, energy is not a vector, therefore negative does not consider there. So it all velocities are positive when you are dealing with energy. So definitely this will not be energy will not be conserved. You can't move from zero to something else and talk about conservation. So fine, that's the good part of it. I hope now we understand that when we're calculating the net force, there's only one formula dealing with the net force. So fine. Also, all real collisions are inelastic, and also the principle of saying the total linear momentum of an isolated system is conserved. So hopefully we are getting better and better as we do questions. So I'll leave you now to do some more questions, and if you don't get it, then you can always ask your teacher as a first line of contact. So I think that will be great. Thanks a lot. Until we meet again.